panelists, who are Dave Moore, Elise Boulicaut Ennis, and Mira Varma. They're going to be giving some presentations on different aspects of science communication, and then we'll have a little discussion after that. And then we'll shift over to the Granville Academy rest of the program. Yeah. And you're all welcome to stay for that as well. It will continue the theme of science communication. I think Meg might give a talk on how not to give a talk, and some other things. So welcome to our Science Communication Day.
Okay, great. Yeah. Hi, everyone. I'm David Moore. I'm a faculty member here. I've been here about 10 years. And I've been tasked with telling you a bit about writing papers and abstracts. Maybe as you're getting started in research, you're starting to think about how you actually write a paper. You'll see I have a ton of PhD comics throughout this talk. So, this, hopefully, I only have 15 minutes, but hopefully I can give you a little more creative ideas than the PhD comment where you just slam your head against the screen until you transmit your thoughts directly under paper. Although that would be a nice way if you could. Okay, so maybe why do we publish papers in the first place? I would say, this is a lot of in this talk is my opinion, and you should talk to lots of people, especially in your subfield. I come from a physics background, so I sit here in Wright Lab. We do nuclear and particle physics, and there's a lot of culture involved in writing papers and how we write papers as a community, because the goal of papers is really to talk to your scientific colleagues about what you've done. And it's one of the ways, maybe one of the most important ways, but certainly not the only way that we convey our work to the rest of the community, maybe in a way that allows them to fully understand, at least in an ideal world, fully understand what you did. And, in science, maybe even possibly replicate. We often have this goal that if I've done something, it shouldn't be just something I can do, but if I've written a really good paper, maybe somebody else can reproduce it, and they don't have to trust me. They can just see the answer for themselves. I think this is also interesting. This is a plot for physics papers. There may be some astronomers and other folks here as well, but I'm sure there's a similar plot for astronomy. You're really joining a community, and a continuously growing community, producing this kind of scientific literature. So this is more than 100 years. This is a Moore's law. Since I'm David Moore, I have to show Moore's law. Number of papers versus year. And it follows pretty much this pretty impressive power law with a doubling time of 6.5 years. You see there's a couple dips for the world wars, but otherwise we're trending up and up over time. And there's now, literally millions of published scientific papers here. This is from a Century of Physics and Nature a few years ago. So every paper you're right is contributing to this amount of knowledge. And, this is a huge...
This is cumulative?
Yeah, this is a cumulative number.
Yeah.
Yeah, so you could take a derivative, but yeah, that's my understanding since cumulative. But yeah, I mean, that's a huge body of knowledge that we've created as a community of scientists, and you're contributing to that with your papers. And, it's an important part of, at least as an ideal, important part of contributing to knowledge as a whole. I will also say much more practically for academia or many things you do, publishing is an important part of your CV for getting future positions and things. People look at, what you've published in the past. Okay, so with that preamble, how do you actually do it? And again, it's hard to say in just a few minutes. This is a complicated process. And maybe the hardest part is just what is the thing you're going to publish in the first place? And this is something you really do with your research group in your topic. Maybe you're already doing research this summer. You want to come up with some new contribution to that literature, something that people haven't thought about, or you're thinking about it in a new way, new analysis, data, something that you think would be a good contribution. This is really where you spend your time typically. And, I would say as you're getting started, the best thing you can do is talk to your advisor, your co-authors, other people in your group to know when something, what chunk of science is publication ready and publication quality in your field, right? And, there's actually, research is incredibly hard, and there's a huge bar in many fields for getting something from an idea to the level of maturity and understanding at which you can say, this is ready to be written up and make a contribution. But, there's also the other side of that where sometimes in particle physics, we might, take 5 years to publish a paper. That's probably wrong. Some other fields like astronomy are better at this and publishing more incremental things and finding the right balance. There's no algorithm to it, and it's really field dependent. So talking to, other people who have done this type of research is really important. Kind of practically, once you have an idea, you're ready to write it up. Maybe you want to pick the journal you're going to submit it to. Again, this is pretty physicsy heavy here. But here's some examples of journals. In physics, we have the Physical Review. In astronomy, there's Astrophysical Journal, APJ, maybe lots of other journals relevant for that. One thing I've highlighted here is that some of these journals are run by nonprofit organizations in blue, and some are run by for-profit organizations. I think every journal I've listed here is very reputable, but if you publish a Nature paper, you might spend up to $10,000 paying them for the privilege of publishing your paper with them. And that in principle, I guess, goes into their profits at the end of the day. So it's something just to be cognizant of. And at the other side of this, there can be some journals that are for-profit and have more of a business model of publishing lots of papers. So again, especially as you're getting started, trying to understand what the journals in your field that you want to target your papers to can be useful. That's especially useful because once you know where you're publishing, there's all kinds of practical constraints that come from that journal. And probably the best thing to do is to look at recent papers for guidance on how papers in that journal look, how long they are. I think in astronomy and physics, we often or almost always write our papers in LaTeX. But some journals I think will accept things in Word, and they'll have a template. If you haven't used LaTeX before, there's this great tool called Overleaf, which allows you to work on LaTeX documents with all your co-authors. Multiple people can work on it. It's like a markup language, like HTML is for like writing web pages. This is kind of a language that allows you to do math and figure placement and everything that many journals are happy to accept. And then there's other things like page limits. Sometimes there's short papers called letters, like Physical Review letters might only give you 4 pages. If you publish in Physical Review A through E, which are the subfield specific journals, you might have as many pages as you want. That can be very constraining. It's much harder to write a 4-page paper than a 20-page paper. You might not think that, but that turns out to be really true, because to say everything you need to say in just 4 pages can be quite hard. And that can really change how you actually write it. I would say once you know what the boundary conditions are and what the paper should look like, you want to outline it. What are the major methods, results? What is the conclusion from your work that really is the contribution that you're making to the literature? People have all kinds of different strategies for doing this, but I think always having an outline, knowing where you're going before you start is good. And sometimes you might write the conclusions first and work backwards. Some people like to write the abstract last. You don't necessarily have to write the paper in chronological order. And then start writing, because there's as we'll say, there's much to do once you start writing. So again, PhD Comics is a great resource for all kinds of things about writing, because it's such a big part of what we do. You could think very carefully about every word before typing, or just randomly type things. And, maybe you want to err on just getting stuff on the page and maybe a little closer to the random than trying to write the perfect thing the first time, because, getting something down in place allows you to iterate on it and come back to that. Okay, let me keep going quickly. You should also stop me. I know I'm going quick, but feel free to ask questions as we're going. This is maybe just to show you the rough structure. Again, it really depends on the journal. You should look at the journal, look at recent papers in your field. Does anyone know what this paper is, if you can see it? It's kind of a famous plot here. The title is probably too small to see, so this is a good quick. Yeah, great. So this is the very first detection by LIGO of gravitational waves from merging black holes. You can see these this is the kind of power they see versus frequency. You see this chirp over time in both their detectors. These are the waveforms. I just picked this paper, I thought, because it's a letter, it's in Physical Review letters, but because it was LIGO, they let them take 10 pages instead of 4, so that's kind of cute. But it has everything you have in a paper. You have, a title, abstract, there's some introduction giving the context for the work, but then the bulk of the paper, and I'm skipping, 8 of those 10 pages here in the middle, it's really the methods and the results, the plots, the, things you want to convey. Figures are really worth 1,000 words, and picking, you can't put too many figures in a journal paper, so picking the right figures that convey the right things is a crucial bit of writing a paper. Myself included, and many of us might put the figures in first and then start writing the text, actually. Many people who read your paper might only look at the figures, or so having the figures really tell a story is great. And then maybe some short conclusion, not acknowledgements, and references. References are really key, because again, you're building on that body of work in your field, and you want to make sure you've accurately accounted for all the work that's been done before that you're building on. So start with a LaTeX template. Don't do it from scratch. This is also, I think, crucial, is to use a reference manager for managing the references. So BibTeX, for instance, or some sort of thing, and you can download programs like Zotero, which is free, or other citation managers that allow you to get the files you can plug into BibTeX and then plug into LaTeX. If this doesn't make any sense to you, definitely ask me after, but there's lots of tools to help you do these references that are gonna make your life a ton easier. And if you're working with more than just you, and even if you're working by yourself, I think almost all of us are using Overleaf now to do LaTeX.
You've lost sound.
Nope.
Are you muted or? No.
Weird.
Yeah.
So, really
Because you can still hear.
okay.
So maybe.
Yeah, whoever can't hear, maybe check.
Maybe.
Yeah.
Leave and come back. Yeah. Okay, sorry for the interruption.
No worries. Should we wait a minute?
No, go ahead, it's okay, I think it's just.
Okay. Yeah, I'll go quickly over this. The start of the paper is the abstract. As I said, maybe you write this at the end of the paper, but it's the thing that, I would, to be honest, like if someone's gonna read your paper, they're gonna look at the title. If the title's intriguing, they might read the abstract. So you really want the abstract, which is just 5 or 6 sentences trying to distill the main ideas in your work. What did you do and what are the conclusions that someone can quickly read? And if they get sucked in by that abstract, maybe they'll look at your figures. And if they're really like impressed, then they'll read the rest of the paper. So that's maybe the order of operations and why these things are so important. You really want to capture the attention of possible readers. You might also write abstracts for talks and things, and the strategy is always the same. So you really want to distill down, just the 2 or 3 things that you want people to know about your paper, even if they don't read it. And for talks, I think I was, also tasked with that. So, it's common for talks to be less specific than a paper. In a paper, you know what you've written in the paper, so you can really be detailed. There's often a kind of practical thing when you give a talk, you might apply for a conference 6 months in the future. We're hoping to talk about work that does not yet exist. At least we do this a lot in our field. You can be a little more vague in a talk abstract and maybe allude to what you will be talking about. And then if, things don't go exactly the way you expect, you can still say something somewhat more generic if you're unsure of your results. But the point of the abstract is to really, tell people what you did, but get them maybe excited. What's the exciting thing about what you're doing? And again, if you take away one thing from this, look at the papers in your field, talk to people in your group, look at the conference abstracts to get an idea of how these things are written. So this is the thing I just said. You want to submit an abstract for a conference in 7 months. I have no idea. Oh, don't worry. The trick is to make it as vague as possible, and then the more ambiguous, the better. And that's why it's called an abstract. Okay. So figures, I'll go quickly, but like figures are really crucial. It takes a ton of time to make good figures. Here's a bad plot and a good plot, at least in my field. Do I know what's wrong with this bad plot or what I've called a bad plot?
First thing is there is no access levels.
Yeah, no labels for sure. If anybody uses root, you might see this as the default root plot without any time or effort put into it. There's not a lot of information density on this plot, so you're wasting a lot of paper space. I claim in my field this is a really good plot. If you're a neutrino physicist, you probably know what this is. This is from Microboon. But yeah, it's well labeled. It actually has a huge amount of data density so that someone in neutrino physics looking at this plot would really know exactly what they saw. And in fact, they would know, unfortunately, they didn't see the new type of neutrino that they were looking for because the data in black doesn't match this red line here. And this plot, I'm sure took whatever student or postdoc made it, a lot of time to really put together and get this level of information density on it. And what's good in your field will vary. And I would say, the bottom line is this takes a lot of time, but is really worth the effort to fine tune your plots.
I ask.
Yep, definitely.
How much is too much information?
Yeah, so that's the other balance, right? I mean, I would say this is not too much because I can see everything on the plot. There's not stuff like covered up, but it is a busy plot. I still think a good plot, but on the busier side. So I don't think there's any rule of thumb, but if you can't see things because there's so much on it or it's distracting for like this thing to me, at least working in the field, really shows me that the data are far from this red line. That to me pops out of this plot. You don't want to put so much on it that you distract from your main point. So it's really a balance and yeah.
So I have a question about color blindness, because I know that, some people, like I know somebody who cannot see green at all, so
Yeah.
they would not be able to see that green.
Yeah.
So in journals, they let you use patterns and things as well as color, or how do they address that?
Yeah, the journals used to really enforce this a lot, is that it should print in black and white and everything be legible. I think they're getting a little looser with that now that there's not printed copies of journals. But I think it's a good idea still to strive for this to be as legible as possible in black and white, and also be cognizant of people with different types of color vision. And many of the palettes, like you can find lots of resources online about good color palettes for, you know, the most typical red-green color blindness or other things. Turns out the Tableau colors in Python are well designed for colorblind people in terms of tone. But yeah, there's really a lot written on this, and I think it's good to be conscious on making your plots as visible as possible to as many people as possible. So yeah, you can see there's a different line style here. Probably this plot looks okay to people who see differently. Okay, let me say quickly on references. I think I might be over time, so let me hurry up. Yeah, understanding the prior literature is really a key part of writing papers. You want to know it's new, and you want to include citations that are right and that you've read and that are appropriate for what you're writing. There's many examples where there's citation bloat. People just like, you know, throw a lot of citations into their work. Sometimes you can't cite every article that matters, and maybe there's review articles that, you know, if you're in a very mature field, give you a comprehensive view of a large body of work. The best thing is if you don't know what papers to cite, you really need to read papers. And there's tools, at least for us, I think in astronomy it might be ADS, the NASA system. For us, it might be Inspire in high energy physics. There's tools that let you work in this web of citations where you find a paper, you see what it cited and what, you know, what cited it. And you can work through that web to really understand maybe relevant literature. And it's important to read these papers. And you know, here's the PhD comment. I added a bunch of references. Great. Wow, did you read all these? Of course. Well, define read, right? Maybe you need to reference the dictionary because, like, you know, it's not just that you should cite it because it looks like it has the right title. You should understand the literature in your field, and part of writing a paper is taking the time to make sure you really do. And what you're citing is most relevant. And then last but not least, revisions are super important. You're never going to write a perfect paper the first time out. There's many stages you review while you're writing it among your co-authors. If you're in a big collaboration, you might have an internal review process. Then you send it to a journal and you get peer-reviewed comments back from an anonymous reviewer. Often they can be extensive and you have to rewrite the paper. And then some cases, even after you publish it, you might have to write an erratum or comment on it if you find something was wrong. And this is one of the biggest time sinks. Like writing the first draft might not take you a ton of time, but then really revising can be the crucial part of getting to a final process. And yeah, here's draft infinity. Finally, once you get very sick of it, maybe it's time to turn it. Yeah. Okay, yep. So last slide, once you're happy with this, at least in our field, typically what we would do is you have this draft, all that revision's done. We would submit a preprint to the archive, maybe in astronomy that's also common, that you put your paper up before you submit it to a journal so everybody can see it. This is a free server where you get these pre-published papers, not yet peer-reviewed, but that lets everybody see it right away. And then at the same time, you submit it to the journal you chose. After several weeks, hopefully it's only weeks and not months, but it really depends on the journal. You get some comments back from anonymous peer reviewers, you revise, address those comments. You typically have to address everything they said, repeat that n times until they're happy, and then the paper is either accepted or rejected by the editor who reads and understands those reviewer reports and whether you appropriately respond to the reviewers. And if it's rejected, that happens. It's definitely part of the process. You could send it to another journal if it's, you know, just they don't think it's the right fit for the journal, or maybe you're going to take more data, do major revisions before sending it back. If it's accepted, great, congrats. The journal will send you one final proof where you do the copy editing, you check carefully for typesetting, and then finally, after all that, maybe in a few weeks, if you're lucky, it's published, probably online. And then I would say you should always update your archive posting with the, you know, not the copyrighted version from the journal, but the equivalent version with all the text and figures. And then you start your next paper. Okay, so let me stop there. Yeah, of course.
Okay, so now we're going to go from papers to conferences and presentations. So yeah, we just talked about sharing your research in writing through papers, but there's also other ways that you can share your research, which is in conferences. So this is where you present your work to other physicists in your field. So in this context, you can be a bit more specific or technical than when presenting to a general public, as Mira will talk about later. But one thing to remember is that not all your audience members will be experts in your field depending on the conference. So when you're reading a paper, you choose to read the paper, you kind of know what you're going into. In a conference, you don't always know, so you might want to be a bit more general, depending on the conference. So I'm gonna go through kind of 3 different aspects of making a conference experience a success. So one, preparing your slides, making sure they're polished, delivering your slides, and then interacting with others during the conference outside of your talk. So just a quick introduction of who I am. So I'm a postdoc here at Yale, and I work on Atlas, experimental particle physics. And yeah, why that's maybe important for this is that in large collaborations like Atlas, we don't always present on our work specifically. Because we're a large collaboration, we can be asked by the collaboration to talk about kind of a review of things that the collaboration has done that are related to our work, but not explicitly what you've been working on. So that's a little bit different in large collaborations, but it's maybe something to be aware of. And so I've included a list of conferences that I have presented at or will present at, and it's actually funny that I'm giving this talk today because I'm presenting at a conference next week, and I've spent this last week preparing conference talk, so it works out. And so you can see here, there's kind of you might not understand what all these are, but there's kind of a wide variety of types of conferences. So the one I'm going to next week is called Higgs Hunting. It's specifically about Higgs physics. And so it's just one part of particle physics. So it's going to be a smaller conference and a very narrow scope. Whereas I also presented at the APS Global Summit. That's all of physics at once. So you can get people from any field. And so that's a very large conference, very broad scope. So you have to be aware of the audiences. Okay, so first, preparing slides. So I'm going to touch on a few aspects that I think are important in preparing slides. The first one is having a clear structure. So when you're preparing your slides, it's helpful to have an outline of what you're going to talk about. That helps you to write it. And then as you're making the slides, you want to make sure that your audience, that outline is clear to your audience. So one way to do that is to have an outline, a specific outline slide, or just have like I did, bullet points in the intro of like what you're going to talk about, and then section headers like I just did right here, to just separate out your different parts. And also number your slides. This is very important, because if you get questions after your talk, people need a reference. If they have a question about a specific slide, they're going to say, oh, I have a question about slide 17, and then you can easily go back. Okay, for the text, so yeah, I would say stick to bullet points or labels around images rather than big blocks of text, because no one wants to read a big block of text on a slide while the person is talking. Like your brain just can't do those two things at once. Use consistent font, just to not distract the eye, and then keep the font size large enough so that it can be seen from the back of the room. Hopefully this is large enough. And then make use of color. Color can be really helpful, but doing it in a meaningful way. So I've seen slides where it's just every line is a different color, but for no particular reason. I like to kind of color code things. So here I've included an example of the slide and the talk I'm going to be presenting next week. So I don't have big blocks of text. I just have labels of what is this plot, what is this plot, what are the results. I've kind of color coded based on the annotations I've made to the plots, and yeah, I tried to put the important stuff in bigger font sizes, and then smaller for the side notes. So yeah, some of these are preferences, but just an example of how you can do things. Animations. So animations can be helpful for drawing the attention to one part of your slide at a time. So again, I'm going to show you an example of a talk I gave a few weeks ago or a few months ago, I was talking about the upgrade of the Atlas detector, and I wanted to kind of talk about the different sections of this detector. So I had kind of the same slide, but I was highlighting different parts of it. So that's an example where animations can be helpful. You can also have text come up at different times if you want to focus the attention on one thing. But again, you want them to be meaningful. You don't want to just randomly have animations because then they could be distracting. So plots, as kind of the same thing as for papers, you want all your plots to be labeled and big enough to read. So again, I've included an example here. I have kind of two big plots on one slide. They have all their labels with units and things like that. And then this is also a personal preference. I like to label plots with arrows and say, okay, this corresponds to this part corresponds to this, just to help people understand what they're looking at. And then finally, I would say it's okay to leave out some details. Usually you have limited time. And so you can't include all the details about what you're going to talk about. So you can refer to other talks or papers via links. A lot of times your slides will be available to the people at the conference later, so they can click the links and get more information. So it's not your goal necessarily to give them all the information at once, just the main parts. Yes.
Speaking of that, I have a personal request for each and every one of you. If you're ever going to a place to give a talk, please name the file with your name. Don't just say Yale 2025. I get so many that are like Yale talk and a date, and I have no idea who these are. So if you include your name at least, that'll be helpful.
Yeah, that's a good point. Okay, so that's about preparing the slides. So next, about delivering the talk. So I would say practice is really important, especially when you're starting out, when this is your first talk or second talk or whatever. So you're gonna want to practice maybe a few times alone, and then in front of others, friends, colleagues, really. I mean, colleagues in your research group can be really helpful because they know the details and they can catch the kind of the technical things. It can be helpful also to practice in front of someone who's not an expert in that field. And they can kind of maybe comment on your delivery or how clear you were, how fast you spoke, things like that. And then you can make tweaks based on the feedback that you received and also the timing. Practicing really helps you stay in time and then be more confident at the conference that you're going to stay in time. Some things to keep in mind while you're giving your talk is for each slide, and then for the talk in general, you want to think about what should the listeners take away from this. You're going to be giving a lot of information, but you want to highlight what's most important. And so you want to make that clear on each slide, like what should you take away? Another thing to keep in mind is that people will likely not read everything on your slide while you're speaking. You've probably noticed that as you're maybe even right now, you're probably not reading every single word of this slide as I'm talking. So that's why you want to make sure to have sparse text, and if people are checking the slides afterwards, you still want it to be clear enough so that it makes sense if you're looking at the slides on their own. But if there's important details, don't leave them out just because they're on the slide, because don't assume that they'll read everything. And then another thing is try to tell a story. So it's that can be sometimes a little bit difficult when we're talking about really technical research, but it makes it so much nicer for the audience to be able to follow that arc and to keep them engaged. You can look at this later, but it's basically you want to reach a climax of, okay, this is the point of the talk. This is where we were getting to. And now I'm satisfied. I understand why you're giving this talk and why it's important. So try to keep that in mind. I know it's not always easy. Okay, and then delivering the talk. So there's a few things that, will make it, will make you a more effective speaker. So be enthusiastic. So conferences are tiring. You listen to a lot of talks one after the other. Maybe you were traveling for a long time to get there. So when you have a speaker that's enthusiastic, who livens things up, it's always nicer. So try to be that speaker. Dress appropriately. I mean, I would say in physics, people are pretty relaxed, but still use common sense when it comes to that. Try to appear professional. Look at the audience rather than your slides. If you've practiced enough, you shouldn't need to look at your slides that much. So looking at your audience is always more effective. And then speak slowly. You know, when we're nervous, we tend to speak faster, and then it can make it hard for people to follow. So maybe be more explicitly speak slower than you think you need to, and that would be helpful for people. Okay, and then taking advantage of the conference. So when you're going to a conference, it's good to prepare a little bit beforehand. So usually there'll be an agenda, so like a schedule of what's going to be going on. I would say check the agenda beforehand and make sure that you plan to go to the talks that you really don't want to miss. Sometimes there's parallel sessions, so there's multiple talks happening at the same time. So you want to make a plan for which sessions to go to. Here's an example of APS, the very large conference that I was talking about before. At any given time, there's probably like 5 or 6 things going on at the same time, or more than that. There's many things going on at the same time. There's hundreds of talks. So yeah, that's one where you really want to have a plan. And then because the point of a conference is to meet people and interact with other people in your field, sometimes they will have a list of participants. You can check that. You know, as you get more advanced in your career, you might start building a network and you know people. And so if you know people at the conference, maybe make a plan to meet up with them. And then also plan to go to the social events that are organized through the conference, because that's a really good way to meet people as well. And then once you're there, attend as many sessions as possible. Even if topics are unfamiliar, it's always interesting to learn something new. Personally, I like to take notes just to keep my mind focused on it. Maybe other people, that distracts them, but I think it is helpful to take notes and ask questions. Don't be afraid to ask questions. It can be kind of intimidating, but you know, if you're wondering something, it's likely that someone else in the room is wondering the same thing. So don't be afraid. Interact with others during breaks and social events. And contact people that you've met at the conference afterwards. This is how you build a professional network, and that's, like I said, the point of the conference. So final thoughts and tips. It's okay if your talk doesn't go well or doesn't go as well as you hoped. You can always learn from your mistakes, and there will be other opportunities for sure. If you give regular presentations within your research group or collaboration, that can be really good practice. You know, just in making slides and delivering them. Then observe and learn from good speakers. If you're at a conference or somewhere else and you notice, oh, that talk, I really understood it, or I was able to follow really well, that person was really engaging, try to identify what made that talk really good and to apply that to yourself. And then I've also included an interesting paper on archive here about kind of the things that I talked about today.
Great. So now that we've heard about both,
Oh, is that? Okay.
Yeah, you should.
oh wait, should I? Oh, I changed the slides. Oh. Sorry about that. So now that we've heard both about commuting science via writing and via talks at conferences, now I wanted to talk about something a little bit different, which is how one communicates science to the general public. And my name is Mira, and I'm a 5th-year physics PhD student and also a co-director of Yale Science Communication, where we organize talks at local venues for the general public to learn about various science topics. So I just wanted to start off with a nice quote that Feynman said, which is that the ultimate test of your knowledge is your capacity to convey it to another. And I know that the obvious answer to why one would be interested in science communication as a scientist, it probably would have something to do with funding or alleviating like taxpayer concerns about paying for all this physics research. But in addition, I really believe that explaining your research to the general public and to people who are not experts at physics at all, like really improves your own understanding of your research. So that's another important reason why one should think about doing this. So when communicating science to a general public, there are 4 essential strategies that I just wanted to briefly go over. Those are to know your audience. So different ages of people and backgrounds of science will require different types of explanations, and it's important to be aware of that and also try to remember what you knew at that stage of your life so you don't over-explain. Also, it's important to remove jargon. So just when we're working on our research every day, there's a lot of words that we use regularly that other people aren't aware of. And sometimes it's hard to remember that people don't know those words, but it's really important to actually explain the concepts and not just use like fancy language that they might not understand. Additionally, backwards design is important, where before giving the talk, you tell people what you want them to take away from this talk so that they're more likely to pay attention. And finally, tell a story. Our brains are actually wired to remember narratives more than facts, so it's important to take advantage of that and actually give a coherent narrative to people. So for the first pillar, which is know your audience, I just thought it would be nice if we had more time, if everyone could try to think about how they'd explain their science to various like ages of people. But since we don't have a lot of time, I just wanted to show an example of how I would explain my work to various audiences. So if I were to explain my work to a kindergarten student, I would say something along the lines of how everything in the world, whether it's a pencil, me, a dog, anything, is made up of tiny particles, and I study those particles. And if I were to explain my research to like a random person at the grocery store, for example, I would probably say something along the lines of how I'm trying to study the smallest particles in the universe that make up everything and figure out the rules with which they behave. And if I were to explain my research to an undergraduate physics student, I'd probably say something along the lines of how I'm testing the rules of quantum mechanics at particle physics energies to see if our theories break down there. And if I were to explain my work to a professor in my specific subfield, I would probably say something along the lines of, I study quantum tomography for HCZ collisions, entanglement-induced thermalization, and general test of Born's rule. So, as you can see, the difficulty and the language builds up as the person becomes more of an expert. So the second important point is to remove jargon, because as I said before, people use a lot of words on a day-to-day basis in their subfield that others outside the field wouldn't know. And it's even worse for the general public, because when we give our talks for the general public, we assume that everyone has a high school education, but not necessarily any sort of college degree, let alone a college science degree. So it's really important to try not to use words that they might not know. So an example of like a sentence I would use to describe my work with the jargon in it would be like, using Bell's two-state hidden variable model, we show how Born rule deviations could arise. This is a really problematic statement just because nobody would know who Bell is, what a two-state hidden variable model is, what the Born rule is, and the whole sentence would just make no sense. But then for the after, like something along the lines of, in quantum physics, we have a formula that predicts the probability of particles interacting, and we're testing if the formula breaks down. Like here, this is a bit more clear just because I give context about how this is quantum physics and explain what the formula is instead of just naming it and assuming that people would understand when they wouldn't. Another important principle is backwards design. So when you're like at the beginning of a talk, it's important to tell people the so what, so that they know why they should care and be excited and listen to what you're about to say. So that's called backwards design because you tell them the takeaway and then you go through and explain the story. And it's really important to be aware of the different types of audience members and what they're most likely looking for in a talk so that you could understand what types of things they'd want to take away from that talk. So a kindergartner doesn't really worry about like money or funding or anything like that. Kindergartners are usually just excited and curious about the world. So the so what would be something to just inspire general curiosity about science. But with a taxpayer, someone at the general public, they're usually more concerned about why their taxes are actually paying for all this physics research. So it's important to actually emphasize like why this could be helpful in the future. And with policy makers, they're also concerned about how this connects to the real world, except with policymakers, they're typically more concerned with immediate like successes that translate to the real world as opposed to stuff that could help us in like many, many years. And the fourth principle of communicating science to the public is to make sure to tell a story. In all the work that we do in physics, there is always some sort of mystery or problem that we're trying to solve. And it's important to actually like, tell a coherent narrative so that people are more likely to remember what you're talking about. So usually a general framework to think about is that first you set up what the problem is, then what makes this problem hard to solve, and finally how the work you're doing is helping solve this. And people like to say that you should frame your work so that humanity could be the hero. It's not like yourself. Like your work could help humanity like become better and do something to like help the world. And there are many different ways to tell a story. And here I show Vaughn's 8 storylines. And you could see that the conflict and resolution and the buildup is all different shapes, but that's not relevant because every single research has a different sort of narrative to tell. It's just important to actually tell that as a narrative. I just wanted to give an example of why like science communication is important and what could happen when it does fail. So like 12, 15 years ago, like a Florida radio host was trying to like joke that there's dihydrogen monoxide in our water, and then it caused a lot of panics and people were like checking their pipes and calling to complain because they thought they'd get poisoned, and it was a whole mess with a lot of people. But it was supposed to just be a joke because H2O is water, but since that wasn't communicated well, and since communicators haven't really like explained chemical formulas in an accessible way to the general public, it just caused a frenzy. And there's a lot more examples of this. So finally, I wanted to just explain some opportunities that you have now to actually communicate science with the public. So via social media, Right Lab has like an Instagram page where they share like various interesting science articles and updates with the public. And also some of the professors here are actually like talking to the public. For example, Jack Harris was on the this podcast to talk about a workshop he was organizing. And I know Sarah Demers' student talked about physics and dance, and there's so many other examples of people. Also, there's conferences both for the general like physics people, but also for just expanding your knowledge of science communication. Additionally, there's policy work. With a physics degree, you could actually go and work like in DC or work for the government and give suggestions on various funding opportunities. And also there's opportunities to write for scientific magazines that various people outside your field would read. And finally, there's teaching which is kind of what I do, where we, like Yale Science Communication, goes to various libraries and teaches people about their work. And here are some key resources that Samantha Pagan was kind enough to give about various organizations where you could learn more about science communication. This first link, Yale Science Communication, is my organization. So if you have more questions about that or interested in joining, please let me know. There are also various workshops and networks of people that are interested in science communication, and also talks about how to actually like write for the public. Thank you.
Thank you. Question?
I just had a quick question for you. When you're talking about like knowing your audience and eliminating jargon, how do you deal with having an audience that has like very different levels of knowledge? Like, do you usually match to like the lowest level of knowledge, or?
Yeah, so with the science communication talks that we give at libraries, obviously we don't know what the audience is gonna know, and there's always a range of people, but we're just told to assume that people have graduated high school and give a talk for someone who has a high school degree and took the general science classes, but that's it.
About the third point that you mentioned about the backward design. So you have like very nice example, depending on audience, how the outcome can change about like, so what are the motivation? So I was thinking about more in terms of the general audience when I'm talking to someone maybe in a grocery store or something like that. Yes, they are a taxpayer, so maybe that's one thing maybe they will be more interested in, but I don't know if it is a general case that okay, every general public is very worried about the tax paying part more, or they are more interested to know, oh, that's a very interesting thing. I want to know more about this. What angle we should like deal with it. So that was my first question, and just a small second part was that for those backward designing, do you recommend to like tell the motivation fast to oh, do you want to know about how this affect the world, and then say the like that, then communicate the science, or make it a story in a way so that like after the story is done, this is the outcome that they're taking. So I have it in my mind, but I'm not necessarily telling them which approach is better.
Oh, okay, so for the second question first, you tell them, then you give the story start to finish. But you should first like tell them just like a phrase, like a sentence or two, just because it's easier to actually understand a talk if you know the main point to begin with. And you do make a really good point about like the general like public having different interests, I guess. When I said taxpayer, in my head I was thinking someone at the grocery store who doesn't even care about science. So I think that people who, the less someone cares about science or knows about science, the more likely they might be to care about the funding. But if someone like has some sort of like appreciation or knowledge of some sort of science, then they might actually just be more curious. So I think it really depends. There's a big spectrum of taxpayers.
I might add, I think the main point is that your general person on the street is gonna want to know, how does this impact me? And that could be funding, that could be, you know, even curiosity for an older person as well, but the impact is the important part. That's probably the hardest part to determine.
And I would say that that's also something, depending on your audience, if it's one person or a group, that's something that you can kind of feel out too. You know, as you start to talk, maybe you will notice if they're more interested in the curiosity part or more interested in the funding part.
I guess I could just like, how important do you think like publishing is as like an undergrad?
Oh, yeah. Yeah, I mean, it's a very complicated question. I think I'd say the vast majority of undergrads who do research don't publish a paper. You know, it's I think hugely field dependent whether it's even an opportunity to you to publish. If you're gonna work on a, I don't know, LHC experiment where there's like just official rules that you have to qualify for publication, maybe there's essentially no chance to publish a paper in those collaborations. In other fields, you know, it might be very common for undergraduates to have an idea and you know, and be able to publish a paper. So I would say it's much more important from my perspective to do like interesting research and have an outcome from that research, even if it's not a published paper. But you know, all that said, as you go farther and farther, depending where you are in your career, at some point you will start to have publications on your CV. And they're one of the important things for kind of demonstrating your track record in research at some point. But I think as an undergrad, you may hear lots of your friends talking about having papers published, and you should just be really cognizant that they might be in a different field or something. And I mean, we can talk since I know what you're working on, but I mean, in some fields in physics especially, it's very hard to publish as an undergrad. I don't know, others should come in too, because there's also no like universal take on any of these things, right?
Yeah, I mean, the other thing with LHC experiments is that it usually takes like at least 2 or 3 years to publish a paper, so that's not usually within the time frame of an undergrad research project. But I think, yeah, I think it's people who are looking at, if you're thinking about, you know, grad school applications and that being important for that, I think if the people who are looking at your application know these things, and so they know these constraints, and I don't think it'll come against it.
Further questions? Anyone online? Seeing none, let's thank our panelists again.